Bonjour, j'ai le devoir de développer un petit essai sur le sujet de safety. C'est nécessaire d'écrire trois techniques ou stratégies. On peut considérer le cas de... On peut faire des tests sur un moteur dans un avion, mais c'est possible aussi d'utiliser des autres exemples, par exemple les exemples plus moins abstraits. Laissez-moi considérer un moment le fait que nous avons un système d'action. C'était une technique très développée dans des temps anciens, par exemple Euclid. Mais cette idée était renouvelée beaucoup depuis le commencement du XXe siècle. Nous avons des axiomes de Peano et aujourd'hui nous voyons que dans le siècle passé on a utilisé des axiomes dans tout le champ de mathématiques et des autres sciences. Et je pense en fait qu'il y a des aspects de fausseté dans ce qu'on a fait, c'est-à-dire que ça ressemble à ce que l'écrivain Panas dans le champ des ordinateurs a dit, une méthode rationnelle, how and why to fake it. Mais néanmoins, si on adopte des symboles formels, ça vous donne ça vous donne un langage de description. Et anyway, it's for me today to try and work with the idea of logic. So I'm having a look at a paper here by Christoph Abt, a denotational semantics for first order logic. And I think there was a famous logician, it may have been Quine, may have been someone else. I think his claim was that you could use first order logic to do anything. And I would say yes, of course he's right. First order logic has computational power. Presumably it has the power of a Turing machine, and if so, of course you can do anything with it. But it doesn't prove that you want to use first order logic for everything, because you may find that you're in Turing's tar pit, which means that just because a Turing machine has arbitrary computational power, this is in a highly abstruse kind of meaning, which is very different from ordinary language. And what I mean by that is you can say that a Turing machine has arbitrary computational power even if the computations that you're going to do couldn't be done even in our universe. They can't be done in the age of the universe, and even if you had the age of the universe, even if you had much longer than that, they wouldn't be able to be done in our universe. Our universe isn't big enough. So if this is so, it raises a lot of questions about the idea of these Turing machines. Let's try and do something with the idea. So he's saying that the thing is that first order logic is so well known since the 1960s because of the work of Robinson, as I mentioned here, and also of course this was computerized in the 1970s, not only by Robinson but also by people like the people who wrote Prolog. So let's just point out for a start that you've got some logic and you prove some axioms, and surely the point is this, that for fairly simple problems like noughts and crosses, maybe even Lewis Carroll's zebra problem, these problems can easily be worked out with Prolog. And it means that you can solve a lot of problems with Prolog that would have been very difficult to solve without it, perhaps. Of course, noughts and crosses is quite a simple problem that can be worked out by hand, but the zebra problem certainly doesn't seem to be an easy one to do by hand, unless you make a special assumption that the houses are in a circle. Well, you can get an easy answer out of the zebra problem. Otherwise, it's quite difficult. So the suggestions that I'm making are that we can use, maybe the axiomatic method is to be used to write up results that you've already got. If you know things already, well, you can check that they can be proved with the existing theorem prover that you've got. Maybe that's a more correct treatment of it. Maybe if they can't be proved with the theorem prover you've got, you break things down. You keep breaking things down until they are small enough to be, the steps are small enough to be handled with current theorem provers. So maybe this is really the approach that we're getting at. Maybe this is the way we should be going. It's talking here about computation as deduction paradigm. I would say that I think we can have a paradigm that natural language is theorem proving. That when people say things in natural language, oftentimes, if not all the time, they're proving theorems. I think that's a very good model. It's a very, very good model. Because often the semantics of a natural language statement requires you to do some theorem proving in order to know exactly what it means. I can't think of an example offhand, but I think that's the case. They might only be simple theorems. In most cases they're very simple little proofs, but nevertheless they are little syllogisms and things that need to be proved. Let's just carry on. We'll try and go on with the second page of apt and see what he's up to. He's talking about using as queries and clause bodies arbitrary first order formulas, and this seems to be suggesting the language Gödel is presumably something more advanced than Perl. He's also talking about some restriction. He says there are two restrictions. He says that the lineage of logic programming, the queries and clause bodies are limited to the conjunction of atoms, and the computation takes place implicitly over the domain of all ground terms. He's saying if you want to loosen up those restrictions, he mentions that other languages have been invented. So he says that the transition from logic programming to constraint logic programming introduced a new element. He's just pointing out that, what's he pointing out? I don't know. He says that in conclusion, constraint logic programming did not provide a satisfactory answer to the question of how to lift the computation process from the domain of all ground terms to an arbitrary interpretation without losing the property that this process is effective. Arbitrary interpretations are important since they represent a declarative counterpart of data types. In practical situations, the selected interpretations would admit sorts that would correspond to the data types chosen for the user. Let's move on a bit further. On page 3 he says formulas as programs.